All right. So continuing with our lectures last week, today we're gonna still talk about MV's center, quantum spin. And the first topic we wanna discuss is Ramsey interferometry, okay? And the second one, if we have time, then we will talk about classical and quantum spin. Okay. And here I'll write block sphere. It will become clear what it means later. All right. So last week we talked about Rabi model, right? You're not here, but there was an online video you can check. Great. So Rabi model, basically two level, ground and excited. They are separated by a resonance frequency or an energy h bar omega 0, but usually we just skip this h bar, skip this constant, we just say they are separated by a frequency of omega 0, right? And then you send in a wave, and for our system, this frequency is, remember this is the angular frequency, so that will be 2 pi times our regular frequency. In our case, it is 2.875 gigahertz. Okay, so our microwave frequency will need to be around this frequency, also 2.875 gigahertz times some detuning, some kind of detuning. Okay, and detuning here I denote it as drive minus resonance. Okay, so last week we talked about this, right? And we talked about also how strong the amplitude is, right? So we talk about also intensity. Okay, intensity, right? And we say that intensity corresponds to photon numbers, and more intensity you have, more photon numbers you have, there's more chance for you to excite the system within a certain amount of time, right? Okay, so the oscillation looks like this. It goes up and then down, right? If you drive it past a certain time, this we usually call pi over 2. Okay, why does it call pi over 2? It will become clear when we talk about the Bloch sphere representation. All right, but so if this is the excited state population, you drive it, you go up and down indefinitely. Okay, and this is 100%. And we talk about, so if this is strong, you drive it to 100% faster, right? Okay, strong, or we could say, this is just, if we increase I. Now, if we drive this to 100% faster, then that means the periodicity is also shortened. Okay. Now, there's another thing we also talk about, which is detuning. Detuning means how far you away from the resonance. When we have detuning, it will affect not only the period, but also affect the maximum height, the maximum population you can achieve, right? And we talked about this last week using a classical oscillator example, saying that when you are off resonance, then after some time, you will go from pushing it to pushing against it, right? And the more you're off resonant, within this amount of time you push against it, it's more frequent for you to push against it. And that period for you to push against it is basically characterized by the beat frequency. So the frequency difference between the drive and the resonance, the beat frequency, which is this. Okay. All right. So it looks like this. All right. So lower, also shorter. All right. So this is just a little recap, and we also talk about the effect of decoherence, right? I told you that this maximum, this naught, 100% and 0%. Those are actually effects of quantum effects, quantum interference effect. Okay, because imagine, let me say it again. Imagine you have, no, not imagine, but when you plot not only the excited state but also the ground state, you will see that it goes like this, 180 degree out of phase, right? All right. Now, at this point, this is the classical. So this 50%, or this 0.5, this 50% is the classical limit, right? When you reach the classical limit, what will you do? At that time, you have 50% population from the so you have two buckets, right? So at that time, you have about the same amount from this bucket and from this bucket, right? And when you continue to drive it, there are two processes. One is you take this away. There are two processes that can affect the population here. One is you take away, so this will be T, so let me just call it, no, sorry. This is not T pi over 2, this is T pi, okay? So T pi over 2, so that's this. So this 50% point is T pi over 2. Okay, so this T pi over 2, the population at this moment will determine how much you will move away from this bucket in the next minute, in the next moment, and in the next second. And also the population from here will come in too, right? So that depends on the population also in the other. So there are two processes that can bring population to the same destination, or that can affect this, right? And then basically these two will interfere. These two processes will interfere with each other, okay? Given that the population, given that they are coherent superposition, okay? The population in the two buckets are coherent superposition. Then such that the two processes will interfere with each other, and the result is it will decide to go up at this moment, okay? But when you reach 3 pi over 2, okay? When you reach 3 pi over 2 point, the same thing again will occur, but the phase of each are such that they will destructively interfere. And so the population will go down, lower, dive under the classical limit, okay? So it all depends on the phase. Now, but if your phase is gradually lost, if the quantum coherence between the two populations are gradually lost, then this oscillation will start to diminish. And then at some point, they will not be able to pass the classical 50% limit. They will just stay there, stay at 50%. Okay, so last time we talked about this. This is the Rabi model, just a little recap. All right, today I want to start with the general solution of Rabi model. You don't have to memorize it, but it's good to see it. Okay, so I want to show it to you. And there are some. It is rather complicated, but there are some good features in it that we will take note of. Okay. All right. So definition. This again is defined. This is the frequency detuning, and is defined here as drive minus resonance frequency. In some textbook, they might have definition like this. Okay. In that case, we need to switch sign in our solution. Okay. But I like this definition, so I'm gonna go with this. This makes more sense to me. Okay, and this is the Rabi frequency, and the Rabi frequency is, of course, the interaction Hamiltonian. Let me just use V interaction. Okay, the absolute value of V over H bar. So this is the strength of your microwave drive, basically. And that can be converted into an energy. So that's associated with energy, basically potential energy, right? So when we write this, something like SV, something like that, right? So when we write down the interaction Hamiltonian, we have this, and this has the time dependence and blah, blah, blah. And at the end, the magnitude of that, and with some kind of time dependence, right? Maybe a pulse, right? But whatever is in the front, that magnitude goes to here. So that is this. That's VI and T, okay? So that's basically a potential energy from the external perturbation. And that energy corresponds to a certain frequency, and that frequency is called the Rabi frequency, okay? So you know that the harder you drive, the higher your Rabi frequency is. And this population oscillation, you can think of it as energy oscillation, okay? Energy oscillation of the system, because the population corresponds to energy, right? And the harder you drive, the faster the energy oscillates, the shorter the period is, right? All right, so this is the Rabi frequency, and this is the generalized Rabi frequency. Okay, so basically just the square root sum of that, the Rabi and the detuning, okay? What else? Okay, 5. 5 is the laser phase or the microwave initial phase. Okay, so in the microwave, we will write. So here we write microwave like this. Sorry, yeah, this. Okay, so this is the driving turn. This is the initial phase. Okay. All right. So it's funny. No, it's not funny, but it's kind of interesting to note that whatever initial phase your microwave has, it gets attached, it gets tacked onto the quantum system. And that kind of makes sense because, when you have a photon, that photon has some kind of phase, oscillating phase, right? And that you absorb that photon, you also absorb its phase. So you can understand it like that. All right. So, right. Right. What else? I think that's all. Okay. So let's observe this formula a little bit. When we have the quantum system in the ground state to begin with, we have this, right? We don't have this term. And we have also this term. So the first terms in both equations, right? The excited state will increase, right? The amplitude will increase because this is a sign, right? Sign is 0 to begin with, and then it goes up, right? Now, you notice that also this phase here gets attached to the system, right? So this is absorption. Okay, this is important for what we're gonna talk about in a minute. Okay, so this is absorption. And then, right, absorption. Yes, good. Now, if you start not here, if you start from here, okay, it's reversed. We have the excited state as the initial state, right? So it's the second term in both equations that contributes. And we can forget about the first term. Now, what will happen if you have 100% excited state, then the ground state will, just like in the previous case, the ground state will start to rise after time 0. And you see, this is an opposite sign with that in terms of phase. All right? This is emission. Okay? So when you have a transition like this ground state to excited state, I'm sorry, ground state, oh, I'm sorry, I got it wrong. I'm sorry. This, my bad. Okay, so it should be like this. So in my original notation, it is this and that. Okay. Okay, let's see. Right. This is absorption. Right. You go from ground state. Wait. Am I doing this wrong? Give me a minute. Okay, I think that's right. Absorption. That's weird. Oh. Emission. Okay, this is emission because we go from excited state to the ground state, and this is absorption. Okay, let me just write. This is absorption. This is emission. Okay, let me just go with this. Let me just go with this and see how it goes. So, sorry, I have to check. But let me just stick with my previous. Okay, let me just stick with my previous notation. Okay. All right. So let's just go with this story, and if I'm wrong, I'll check. If I'm wrong, I'll let you know. Okay. But emission, if you emit a photon, and it's like a recoil, so you have the inverse, you have the phase opposite, you have the opposite phase. Okay. All right. Okay, now. Okay, where am I going with this? Okay, Ramsey interferometry. Okay, so what is Ramsey interferometry? Okay, I see. All right, so in order to, in the experiment, you will ask to sweep the frequency of the microwave in order to find its resonance frequency. And as you can expect, I mean, this is also, I asked this question also in our previous lecture during the quiz. So I asked the spectrum, right? Excitation spectrum. Is the excitation spectrum line with determined by its natural lifetime? Remember? Okay. Okay, now, in most of the case, without complicating the issue, in most of the case, this width is determined by your pulse duration. Okay. So this, oh, by the way, the tau here is the pulse duration. Okay. So this width is determined by the pulse duration. And this is called transit broadening. If you use a short pulse, it broadens. If you use a shorter pulse, it broadens even more. Okay? The peak is always the resonance. Okay? But depending on how long you drive it, this will broaden. The longer you drive it, the shorter you drive it, the wider this is. Physically, this can be understood through the energy, the frequency spectrum of the wave. Okay, so this is the wave. So if the wave have a central frequency, a carrier frequency, omega, right? Its Fourier transform of that is 1 over tau. Okay, or 2 pi over tau. That's its spectral width. And if you have a very sharp resonance, right? This means when I sit here, see this spectrum over here. So this is omega, and I have this width, right? When I see this spectrum over here, there's a slight chance for it to be excited because it's within its tail, right? It has a it's a broadband drive. When you use a short pulse, it's basically a broadband drive, and that broadband, the tail can cover the resonance frequency, and thus you have a little excitation. And when you get closer, you have more spectral component in that frequency, and thus you drive harder, okay? So it's really the spectral density that goes into the Rabi frequency. All right, now, if you make this pulse longer, make it approximate a monochromatic wave, a single frequency wave, what will happen? According to the Fourier transform, this will become sharper, right? When this becomes sharper, there's no chance for this to be excited, right? So you will have zero excitation here. In this case, at the end, your spectral width will be much smaller. Only when this gets really, really close to omega 0 to be within its bandwidth, there'll be a chance for excitation. Okay? So in order to, so if you have like an unknown quantum system, and you want to find out its resonance frequency, because that's all that matters, right? A quantum system has no other parameter but resonance frequency. That's the only physical parameter in your quantum system that affects everything. It determines a lot of things. So you want to find out its resonance frequency. What are you going to do? Are you going to use a long pulse or a short pulse? When you do the experiment, right, and you don't know where to say your microwave frequency, you don't know where to set your microwave frequency, right? There could be a large range where you're gonna set it. You basically you will find a little window, and you'll scan it, and if you see nothing there, you scan the next window, right? That's basically what you would do. But hello, co-chair. You can sit in the middle if you want. So, so besides the frequency range, so you can probably, so if your device is capable of scanning, say 500 megahertz, so this is 0, this is 500 megahertz, right? You might choose to scan this, and then this, and then this, and then this, right? But there's also your step, right? You're gonna sample it very, very densely, do 100 measurements per chunk, or are you gonna sample it very sparsely? Well, this affects your data acquisition time, right? All right. So there is this range you need to choose, and there's this step you need to choose, right? In order to save time, what kind of frequency? So there are two physical parameters in the pulse. There is frequency and there's pulse duration, right? Like when you do the experiment, there are two parameters, and of course there's amplitude, that's intensity. But basically we typically just fix that to the maximum. So basically what to choose is frequency and pulse width, right? So what kind of pulse width we're gonna choose? Short one or long one? Long or short? Raise your hand if you think we need to choose a short one. Short one. You raise your hand if you think we need to choose a long pulse. Duration, right? Long duration. Short duration or long duration? Short, raise your hand if you think it's short. We should choose short. Short. Raise your hand if you think we should choose long. What happened to the rest of you? Huh? Are you in a superposition? No idea. Okay. Raise your hand if you have no idea. Okay. Then that's still you two. What's going on? What do you think? Then you think it's short? Okay. What about you, Mark? You think we should use a short pulse or long pulse to search for parameters? Short or long? Short? Yes? Okay, I'll take that as an answer, short. Okay, we want to use short pulse to start with. Why? Because short pulse give you a broadband coverage. So you don't need to sample very densely, right? Effectively, your one sample samples like this whole, a third of the chunk if you use a short pulse. Yeah? Okay. Now, suppose we find that the resonance is here, okay? And you see a spectrum like this because you use a short pulse, so it's like big. Okay. This top here is, kind of flat. And you don't know exactly that, because it's also points, right? It's also points. You don't know exactly the resolution depends on your sampling rate. Okay. So if you sample like this sparsely, what will be your true resonance frequency? Well, we don't know because it's our curve is like this. Right? We don't know. If I sampled hard, if I sample denser, maybe there will be a point here, and that is slightly higher than this point, right? So how do we determine the true resonance, the true resonance frequency? Huh? We need to use longer pulse. If we use longer pulse, then this will become, the change will become more strong within the short frequency range, and it will make the resonance stand out more. Yeah, like here the resonance doesn't vary much, it does not distinguish itself from other off resonance because we use a short pulse and it's kind of flat here, right? But if we use a long pulse, then it will become like this, and the difference and you don't need to sample it very, very densely. The difference between neighboring frequency will be pretty clear. You'll see like a big jump. Okay, so we want to use a long pulse. Okay, how long? Continuous. So you never get to finish your experiment, right? Because one measurement will take like forever, 3 hours. Yeah, and also the device stability is an issue too. Can you output a wave at this frequency for so long? I mean, these are practical issues. And that's what motivates Ramsey interferometry. Okay? The original, I call this Rabi spectrum because it used a single pulse. Okay. the original method, brute force, just keep extending your pulse duration until you reach the, like monochromatic limit. That is unpractical because this natural lifetime could be like super, super, super short, super, super, super narrow. And in order to reach that, you need to like make your pulse so long, like for hours. Okay. Device stability is the issue, and data acquisition time is another issue, blah, blah, blah. Okay. So Ramsey was pondering about this problem, and he was trying to find out a way to improve this. He wanted to see if there's a clever way to overcome this limit, this transient broadening thing, right? Yeah, because as long as we have to finish this experiment within 4 hours, our pulse cannot be longer than 4 hours. So there's a limit, limited by the 4-hour transit broadening. Okay, right. So Ramsey come up with a really super brilliant idea. And this is at the core of quantum effect, or quantum interference. Anyway, so Ramsey. Ramsey say, I'm gonna use 2 pulses instead of 1. Okay, so instead of a long pulse like this, he's gonna use 2 pulses, 2 short pulses, like that. Okay, with the separation of that long pulse you want to use. Okay. And of course, this cannot shorten your data acquisition time, because it still takes this much time, right? But at least the device stability issue can be overcome, because you don't need to turn on the pulse for so long. You turn on it for a short while, and then you turn it on again. Okay. Almost. So that's basically the idea. But we will talk about some detail later. All right. And why would this work? Because the pulse he chooses here is a pulse that will split the state evenly. This is called the pi/2 pulse. Pi/2, not half pi. Some people pronounce it as half pi. No, it's called pi/2. This sign is over. Pi/2, okay? So each pulse he chooses is a pi/2 pulse. And the job there is to split the state into 2 states evenly, okay? And if you do this twice, let me just write it here. Excited, ground. This is pi/2 pulse. Right? If you do it twice, after some wait time, if you do it again, like this, okay, so this is E. G, If you do it again, it will split the two superposition states. And what's the outcome? If you look at this diagram, can you expect what the outcome is? What the outcome is? No? Interference. There are two pathways to reach the excited state. Right? Yes? So basically, you either reach excited state at the first pulse, or you reach excited state at the second pulse. So there's this superposition of excitation, two excitation paths, right? The first is effective, the second is not, or the second is effective and the first is not. Right? Your input is G, your outcome is E. Okay? Yes.
Why can it go from ground state to ground state down to ground state?
Because each pulse has the ability because we're using a pi over 2 pulse, and pi over 2 pulse will remember the Rabi cycle? This, when we reach the maximum population in the excited state, that's called pi pulse. Okay, we will discuss why it's called pi or pi over 2 later. Okay, just remember, when you reach the maximum, it's pi pulse. When you reach the half point, 0.5, it's called the pi over 2 pulse. Okay, so when the ground state, so this is the ground state. Sorry, this is the excited state. So when the ground state goes under the excitation, the ground state is put to 50 excited state, and 50% excited and 50% no change. So that's the whole idea of quantum mechanics. You can have superposition of distinguishable states. Okay, and this superposition is achieved through excitation. Classically, you would think, okay, so this is marble, right? Here. And when you perform an excitation, you move a marble from here to here, right? You expect that definitely as time goes, this will just go down and down and down until you reach 50%, the 50% limit, right? But quantum mechanically, the excitation is a matter of chance. It's not deterministic. Okay? So quantum mechanically, when you are trying to send, when you try, or just think of it this way, when you send a microwave pulse to the system for some time, right? There are 50% of chance that the system will absorb one of the quantum state and be excited, fully excited. When it absorbed, it will be fully excited. Okay? But if it does not absorb, it will stay in the ground. There are only two possibilities. Yeah? And so quantum mechanically, if you drive it for this much longer, there will be 50% here and 50% here. That means if you try 100 times, if you try experiment 100 times, you will see for half of the time, half of your trials, you see your system is fully excited. The other half, it is not excited. When you are in a quantum superposition, but you make a measurement, you fall into 100% this or 100% this. Okay? So anyway, so this quantum mechanical superposition is only superposition before a measurement. When the measurement is taking place, it will collapse into 100% of this state or 100% of this state. And how many times? So, and if you repeat, so this is the ensemble interpretation of quantum mechanics, or a probabilistic interpretation of quantum mechanics. And the easiest way is just to imagine you have done the same experiment many times, and then each time you just take a measurement. 50% of time you will find yourself in a ground state. So that means you are not absorbing any photon. It's not effective. And the other 50% of the trials, you will find your sample in the excited state. Okay? But before your measurement takes place, before you take a measurement, this is in the equal superposition of both. Okay? So that's what pi over 2 poles does. Pi over 2 poles split this to equal superposition and this into equal superposition. Okay? With some kind of phase, I think. Here we have a minus sign. Oh, sorry. Here we have minus sign. Okay. So that's phase. That's pi phase. All right. So coming back to this. So when you use two pulses, right? This pulse can be effective or not effective. It could be both. Okay. So the time when it is effective, that will give you an excitation. And you kind of just stay there. Right? G to E. And the time when it is not effective, but the second one is effective, that also gives you the same end state. Yes? The same final state. So that's this. These two paths can interfere with each other. Yeah? The two paths can interfere with each other. And the outcome, whether the interference is constructive or destructive, outcome will determine whether you have a lot of population here or no population here. Okay? And the same goes with this ground state. So let me just move this to here. Okay. So there are two ways I can reach ground state. The first way is I am excited, and then I am de-excited. Okay, that's one way. The second way is I'm not exciting anything. In the first pulse, I'm not exciting anything on the second pulse. Both pulses have no effect on me. Okay, and these two will give you a final state of ground, and they could be in superposition too. Okay. So this will result in also in quantum interference. And what is that useful to our problem? Why is that useful to our problem? Okay, I'm gonna just erase this part. if you're familiar with optics, you see that this is actually very similar to an interferometer that we talk about. So this is mirrored. This is mirrored. Right? So we have a beam splitter. So we have a beam splitter that's split into this component, this route, this path, and that path. Sorry, here. At the second beam splitter, this path can be split further into two. I'm sorry, this is wrong direction. Should be here. Can be further split into two, and this can be also split into two. Right? When I have a detector here, the detector can detect light from this route, from the black route. Or the detector can receive light from the first route, from the blue route. Yeah. And these two will interfere with each other. Right? Your probability or your intensity is E1 plus E2. Correct? Yeah? Okay. And if there's a phase, so say if somehow there's a phase, like a delay stage or something, that change this path length a little bit from this one, from the other one, then there will be a phase attached to this one, right? And the phase will control whether the two are constructively interfering or destructively interfering. And the outcome will be a function, a cosine square function of phi, right? So this is just the basic optical interferometer, right? This is a quantum interferometer. We have the first beam splitter, two paths. We have the second beam splitter. Each path will further split into two. You see that? The port, so this is, you can see this as the ground state port, and this is the excited state port, okay? The port is the ground state and the excited state. So they can be two paths to this port or two paths to that port. Yeah? And the chance we find particle in this port is a superposition of, so let me say, this is GEE, GEE, yeah? And this route is GGE, GGE. So two different paths, right? So this is exactly the same. And the phase difference between these two paths. So you can expect that there might be some relative phase between these two paths, right? Because they are probability and amplitudes. They are complex numbers, so they could be phase. The phase difference between the two paths will give you cosine square. Yeah? This is called Ramsey interferometry. Basically, this is the quantum implementation of an optical interferometer. Last time we talked about this as, this is called Mach Zehnder. Mach-Zehnder interferometer. So this is for optics. The quantum mechanical implementation of Mach-Zehnder interferometer is the Ramsey interferometer. Two-path. Okay? Good? Yes?
What affects the phase?
What?
What determines the phase?
Oh, that's a good question. So what determines the relative phase? We don't have a real space path to travel through, right? So what determines the phase? That's a great question. So we're gonna talk about that now. Okay. I'm happy that you're curious. But before I go further with the math, let me just give you another qualitative explanation of the Ramsey interferometer. So a two-path interferometer could also be seen as a double slit diffraction, right? So when we have in optics, right, or in matter wave interferometer, remember the famous electron double slit experiment? You cover one slit and you see what will happen. You cover the other slit and see what will happen. You open both, you see what happened, right? And you do it one electron at a time. So that's the famous electron double slit experiment. But anyway, so we're not unfamiliar with double slit interference. We know that when we have a wave that looks like this, the wave can go through either this or a photon can go through either this slit or that slit, right? And if we choose to measure it at a specific location here, then there could be two paths, this path or that path, right? And the path difference determines whether I have a high chance to detect a photon there, which translates into intensity, whether I will measure high intensity of photon here or low intensity. Do I see a peak or do I see a node? Remember? Okay, so this is constructive interference. This is destructive interference, so it goes like this. Right? This is a double slit interference pattern. This envelope here is given by the single slit diffraction, right? If you open this, you see an envelope. If you open only this, you see also another single slit envelope, right? When you open both, the two envelopes are in superposition, and they will interfere and making these fringes, interference fringes. Okay, good. All right, now, having this analogy, this tool, now it becomes possible for us to think about what happened here, coming back to our original problem. Yeah? Do you know that the spacing here determines the fringe width and also the fringe spacing? When you have long separation between the two apertures, your fringe becomes narrower but also denser. Yeah? When you have them very, very close, like this become broader. And also there are only few fringes in one envelope. Okay, so that's the basic of double slit diffraction. The same goes, exact same math goes here too. This separation will determine in your spectrum, in your excitation spectrum. So instead of this, sorry, first, this single pulse will give you an envelope. Okay, that's the Ramsey envelope. Okay, this will also give you an envelope. That's the Ramsey envelope. Okay, so you can imagine that I have two single poles, and they are broadband, right? So in principle, I can be excited at the first round by this much frequency components. And at the second round, I can be excited also by this much frequency. And they are in superposition. The two processes are in superposition. So as a result, they interfere. Okay? So, and the width of this as well as the separation is 1 over t, or 2 pi over t. Okay, depending on if you're using angular frequency or just regular frequency. And this is the original, the Ramsey wave. Okay. And that's basically the pi over 2 pulse length. Yeah. Okay. So our spectrum goes from, so instead of having one big lump, we have two big lump, and these two big lump are in superposition, and they interfere, right? And the result of the fringe, the characteristic width of the fringe is controlled by how far the poles are separated. The further you separate the two pulses, the narrower the fringe is. And that is exactly what we want, to narrow down the resonance frequency. Because this thing, you see, this is like super sharp compared to this big lump, right? And this you can just keep on going and going, and it will become sharper and sharper. So when it becomes like super, super sharp, you can really narrow down your resonance frequency. All right, so that is the beauty of Ramsey interferometry. All right, okay. Now let's talk about derivation, because there's also the devil is in the details. Have you heard of that expression? The devil is in the details. So I just gave you a very qualitative explanation or description of what Ramsey interferometry is, and if you buy into the story, you will think, oh yeah, this of course this will work. This is just double slit diffraction. But the devil is in the details. If you don't derive this for yourself, you don't know how actually you can implement this. Because it's not as easy as it seems. Okay. Let me just use, we can start with the excited state and go through this, or we can start with the ground state and go through this. It's the same thing. Okay. It's as you can imagine, if you go with the excited state, if you go with the excited state, then it goes like this, right? They are 180% out of phase because the sound needs to be 1, right? So of course they're gonna be 100% out, 180 out of phase. Okay, so it will suffice to just do 1. Okay. G. Okay. So when I have the first pulse, by the way, let me just say that if you don't do anything to the system, if you don't touch it, then it will be in in a state like this, right? Whatever you have for initial will stay there, right? But there's one thing you need to take. It is true that the population will not change, but there will be phase accumulation in the excited state. Okay. Because we define, we say the gap is omega 0, right? This could be a result of energy to energy, right? This is a result to energy, and the energy, and since only the energy gap is physical, its absolute value is like potential energy. Its absolute value is irrelevant. So as long as the gap stays this, you can make this whatever you want. So if we make this 0, and if we make this omega 0, then only the excited state will accumulate phase all the time, and G will not. Okay? If you choose to have a non-zero offset, say E0, then this will be 0 plus omega 0, right? Then this will accumulate a phase at this rate, and this will accumulate phase at this rate. Okay? And you see the relative phase is this. And since only the relative phase is important for any of our measurement, right? Because when we take a measurement, we take a probability, we take a square absolute modulus, right? And whatever is common, the common phase, you can factor out, and that just goes away. Okay, so conventionally, we just define energy for ground state to be 0, and excited state to be omega naught. Okay, so when you don't do anything to the system, if it's not perturbed, it will still accumulate phase if it has some population in the excited state. Okay, just want to make that clear up front. All right, so from this point to this point, we wait some time. Nothing is done to the system. Since it's G, it will not accumulate phase. Okay, and at this point, we apply a pi over 2 poles. Pi over 2 poles. And this will go like this. Okay, this is excited. By the way, this is G2. And this is excited. This is not excited. Okay? All right, well, a quick thing. So according to that formula, you can check for yourself, but when you apply a pi over 2, this is the solution. So CG will become half pi. No, sorry, will become 1 square root, 1 over square root of 2. So they will be equal position and they'll be in phase. Okay? But when you do this, they'll be also equal position, but they will be out of phase. Okay? Okay, so let's just keep this as our note on the side as we do this, because we care about phase, right? Okay, so right? So going from G to E, we have 1 over square root of 2. Going from G to G, we have 1 over square root of 2, right? No problem. Great. Now, this is this time. So this is my time. This is my time. So my time is, okay. I start my excitation. I finish my excitation. So that's tau. Since I have E population, you accumulate a phase of minus omega tau, right, for this period. As soon as I have E, this phase will start to accumulate. Okay, so I accumulate this much phase after this much time. Now, if I wait for P, okay, I will accumulate another phase. Yeah, for this much time. Up to this point, okay? So that's what happened to E. For G, nothing happened because G does not accumulate phase. So this waiting time, you do nothing to it. This accumulate this phase during this time. It has accumulated already this much phase here. I'm writing only the new phase that is accumulated. I'm not writing the accumulated phase. Okay, so the additional phase being added to the excited state after this much time. Okay. All right, now we're going for this guy. So when the second pulse comes, this will get excited. Okay, and here will get excited, and we'll leave this. We'll not consider that for now, and this will another pulse. Tau, okay? And this will not excited. Okay, so minus 2. So this goes to the excitation, but we will consider the part that when it does not change. Are you following? Are you following? Is everybody following? This is not easy. Excited state start to accumulate phase during the first pulse. Okay. And that's the coefficient coming from here. After this time, it can accumulate that much phase, and after this time, it can accumulate this much phase. And this is the coefficient. So note that there's a minus sign, so that's a pi phase. Okay. So even the pulse is not exciting it changes phase. Okay, that's kind of tricky to think about. Okay, and the other path goes like that, right? Okay, now, so it goes to here. Now here's a crucial part. And I need you to pay attention to this. How I control these two pulses matters a lot to the outcome. Because remember, we said that the phase, the initial phase of your microwave, when you absorb it, like in this case, when you absorb it, you take it with you, right? So this pulse and this pulse, although they look almost identical, they actually are different. Okay? If I draw them, if this is the first pulse and this is the second pulse, if I draw them out, the first pulse, it could some kind of, so I'm going to use FT to represent a top hat pulse shape, okay? So this means if this is time 0, this means it oscillates like this. And I shut it off some point, okay? Now, if the second pulse, this is the first pulse. If the second pulse, if you shut down your device and then you turn it on again, then you will start with identical. You will start with an identical pulse, like that. Okay. In this case, it wouldn't work. It wouldn't work. Experimentally, so in the quantum spin lab, the software was designed so when you have multiple pulses in the software and you choose to turn it on after some time, the way the machine does it is it turns off the microwave generator completely during this wait time, and then you turn it on again. So the two pulses are identical. Okay, so if you start with identical pulse, that means initial phase 0. So this has initial phase at 0, and this has initial phase at 0. If you just start with, if you just take this, let me write down. So the first path is this times that. So I'm writing down the phase times this. Okay, times this. Times this. Right, that's the first path, right? Okay. So this is no problem. There's no problem. This does not involve the second pulse yet, right? Because the second pulse is not doing anything on this path. The second pulse does something here. Okay, let me just write. So say if I have this phase and it get attached to here. All right, so this is the initial phase of the second pulse. And we can set it to 0 to do that case. Okay. So this is 1 over square root of 2. Nothing. 1 over square root of 2. This. And this will also, by the way, this will also accumulate because this is excited state, right? So it will also accumulate this phase, just like in this case. Remember when G to E accumulate that phase. And this is just from the microwave field. Okay. All right. Now if I work out the math and take the probability, it will become a mess. All right. Yeah, it will become a mess. It's very complicated. If this is 0, there's no chance that you will have a simple form. Let me just write. Let me write 0 here. 0, 0. Okay, you can take this as an exercise for yourself, and I can guarantee you that this will not give you a simple form like that. Okay. So the right way to do this is to actually keep this on. Keep your microwave generator on, but you have a separate switch that kind of produce an envelope. So really what is happening is that you need to have a continuous wave that is on, and you have a switch that turn it on, shut it down, and turn it on. But the initial phase here and this initial phase here and this initial phase, they are separated by omega t. You get it? Okay. So here the initial phase is 0, but here the initial phase is not 0. Here the initial phase is omega tau plus t. Are you getting it? Okay. All right. So this is omega tau plus t. Yeah. All right. So if I have omega tau plus t, okay, then you can factor this out. This will be omega tau. This will also give you a factor of omega tau plus t. Okay? Yeah? So, sorry, there's a minus sign here, I forgot. So this will become 2. So 2 square root, right? Minus t plus yeah. If you're familiar with what is this? This is sorry. Forget about it. Okay. So starting with this, if you take the probability, you take the modulus of this, right? This goes away. And this, if you just do individually, so this one, the modulus of this is 1. modulus of this is 1, right? And you take the product, okay? And the product is, and there's also the conjugate. All right, so you guys have to, if you're interested, I give you enough detail so you can work out the math. So this is the conjugate, and basically it looks like this. All right? And this will become, after 2 steps, will become this. And magically, this is the psi square detuning times tau of the initial phase. Okay? Yeah. So basically, this minus this, I give you this vector. If you take this 2, I give you this 2 vector. So that phase goes to here, and that's the square root of that. So this modulate. Okay. If you take, this whole equation and you try to do the full derivation, so this is kind of just hand waving derivation. If you take the whole equation, you will be able to see the envelope being. So here we give you this, the fringes. The envelope will come out if you also take into account of, because here we're doing, we are not, so we're just accounting for the phase, basically. Okay, so if you do more, we are neglecting a lot of terms. If you do more, you'll be able to recover the single slit diffraction envelope, and so that will be the super. So that will be the single slit envelope times this fringe, and that's basically a double slit diffraction pattern. Okay. Okay. So yeah, the real derivation is more cubism and pages over pages. All right. So I won't share it here because we don't have much time. But that's basically the idea, okay? That's how the phase works out. The important thing is this cannot be the same phase. The second pulse cannot be the same phase as that one. It must start with something else, some initial phase that is a continuous accumulation. Some initial phase like that, and then it does this, okay? All right. So we cover Ramsey. Ramsey, and we are, how much time? Oh, great, 90 minutes. Not too bad. We're not doing too bad. Yeah, 90 minutes exactly. Okay, so I'll stop here. I'll leave this for another session. Okay, because this is also a lot of materials. I'll leave this for another session, but hopefully this will help you understand the experiment that you're doing, okay? And the reason we're using the MATLAB script is because we want to have a continuous phase. And right, we want to have a continuous phase. If we just use the spinflex default, it will give us an identical phase, which is 0, okay? So here comes back to our original question. So we want to avoid long, so like there are 2 problems with the Ramsey method, right? One is device stability. One is long-time data acquisition, right? Acquisition. Okay, with this method, it looks like we are still gonna have to wait for this long. But earlier I said, well, but it looks like we bypassed that device stability issue. But now I'm telling you that the microwave needs to be turned on continuously in order for this to have like the correct initial phase. So it looks like we're not getting anything. Now, so if we know exactly our microwave frequency, which we know, and we know the exact time of our pulse and the wait time, then this is basically just a phase number, and this is between 2 pi and 0, right? So we can, by adding just initial phase to our second microwave, we don't have to turn it on continuously. We can just add initial phase to the second pulse, and then it will work just as you have it on continuously. All right. So we still, so by this method, we still bypass the device stability issue, because now we really shut off the device in between. Okay, but we have to keep track of the phase accumulation at the price of tracking the phase accumulation. Okay, cool. Good. Okay, so this should be, I think this is 4. All right. Okay, time for quiz, for a little quiz. Time for a little quiz. Quiz. All right. I have only one quiz actually, because I prepared 2 quizzes for each topic, but now since we only cover one topic, so I'm just gonna give one quiz, and this quiz is kind of obvious. Can the pulses used in Ramsey and parametry start with the same initial phase? All right. Yes? Oh no. All right. Shouldn't be too hard. If you know what that means. Okay. Obviously, everybody's paying attention. Great. All right, thanks. You're dismissed, and you can go to the lab and work on your experiment.